Okay, good afternoon, and thanks for the introduction and for this wonderful meeting. Are we deep networks? I will go into the details as we go along. A little bit of history of what is happening now. We heard a little bit about it. I will expand upon this, and some of the successes, but also some of the limitations of what seems to be very difficult to still get by artificial intelligence systems. How does it compare with the brain? What can we do differently? So all of these things are starting with describing what's going on, but it's becoming more speculative, but we'll see as we go along. So a very brief history of how we got to these exciting times where things are really changing very, very rapidly. It started, as Tali already mentioned, with Alan Turing, maybe some other people, but this was quite an amazing start with Turing, which in his famous paper in 1950 on computing machinery and intelligence really started the field. It's a very clever and very interesting and very accessible paper, so people who haven't read it, it's something that it's not only for the experts, and it's pretty amazing and full of insights and trying to define the problems and ways to get ahead. So it started then, but there were almost no computers around and very few people thought about computations and what to do with it. So it took quite a long time to start to develop artificial intelligence. I will not go into this history, but mention the first success with its success and limitations. That's the famous event in 1997 where the computer built by IBM, Deep Blue, managed to beat the then reigning king of chess in the world, Garry Kasparov, who is really one of the greatest players in the history of the game. This really made AI suddenly a household name. It surprised Kasparov, it surprised the experts as well. It was really quite an event. But this was a very specific task and very special machine. It took about 10 years to accomplish this feat by maybe 100 engineers or so. In fact, a combination of engineers and chess experts that together teamed up in order to build a very specialized chess-playing machine. The next and somewhat different success, very notable success, was in maybe quite a bit later in 2011, when the system called Watson managed to beat the world champions in the world of Jeopardy. So I don't know how many people here know and appreciate what this means, but Jeopardy is it's probably the most popular TV game in history, Jeopardy, and it's sort of a generalized quiz, a knowledge and understanding quiz, and this makes it more interesting because it's not very specialized. It's really testing experts or about general knowledge and understanding, and Watson competed with human experts on this task, and it was, I think, a 2 or 3 day event, and the computer won. And Ken Jennings, who was he was the world champion, the human champion, who won 74 competitions in a row without losing anyone, but lost to Watson, and he was very gracious, he's very nice, and he said, I welcome our new computer overlords. So I don't know if they were overlords, but this was already an interesting, as I said, an interesting development because of the openness of this challenge compared to pure chess playing. The big revolution came from the field of computer vision, which is the field which I'm most closely interested in this area of, in this domain of artificial and human intelligence, the way we understand what we see around us. And computer vision became a very organized field, and it has sort of a yearly Olympic Games, and they are very well organized, and people participate, and there are challenges which are put out by the organizers of whoever volunteers to organize such a challenge. The most well-known and with most participants was something called ImageNet, which was a competition in recognizing objects. You got from the organizers of the competition a few million images of different objects on which you could train your algorithm, whatever algorithm you want to develop. And then you send in your algorithm, and the results are evaluated on a secret set that nobody sees, but it's kept separately. And then it's possible to see who did how well on the set which was kept secret and nobody trained on. And every year the winners are announced, and there is a small ceremony, and then people get a gold and silver and bronze medals and even a monetary prize of $100. But it's a big deal to be a winner in this community. It requires more and more sophisticated algorithms and things developed in time and sort of asymptoted. And in 1912, suddenly there was a new entry with an algorithm which was called deep learning, and it managed to beat all the competitors by a pretty large margin. So it was very noticeable. People who were in the field were struck. Here is, after many years of trying to improve, here is something that makes things noticeably better. And the really sort of special part about it, the same algorithm, deep network, without any changes, the same code, was also sent to a sort of brother or sister competition in the area of speech recognition, which really requires a different set of algorithms, it's a different expertise, and it won the other event, the speech competition, by about the same margin. So this, people who are interested in artificial intelligence and learning and so on, they couldn't ignore it. Suddenly this new algorithm arrives and wins these two competitions. This is an example, so you get sort of the complexity of things that it had to deal with. This is one of the many object classes, elephants in this case, and you can see that it's really very variable, and new images that you're going to be tested on are going to be within this class, but can be very different. And what was especially interesting about this new approach, this new set of algorithms, is that it's completely automatic learning. So there is you do not put in lines of code that are specific to vision or specific to speech. It's the same thing, it's the same algorithm that accepts the training images and produces for you the algorithm that eventually will be used in order to win the competition. So no manual feature extraction or understanding and so on, it's all being extracted on its own by the automatic learning. And this requires big data. And you'll see this again, it was mentioned before, but it's an important aspect of this entire domain that you need to train, in this case, of millions of images. People mentioned here already, for example, the Google very high-performing system for recognizing faces, but it was trained on 240 million images of people in order to reach this level of expertise compared to what a normal person would see around in order to recognize faces. This caused quite a lot of excitement, both in the more technological areas, but there is really interesting aspects of science about it. We heard a little bit about it throughout today. So it started to appear in the new developments in this and the principles behind it in science and nature, and it started to become a very interesting area of scientific exploration and development. You saw a little bit about why they are called deep networks and a little bit about the relation to the brain. I think it's interesting, certainly for a crowd who comes from people who come from brain research, that this entire wave of new type of learning algorithms and machine learning was really motivated by what we knew as basic principles of operations in neural networks, especially in the cortex. They tried, and this was sort of a bet or a guess, that there are certain principles are more important than others. So they created already in the 1980s, people who worked in this field simplified neural networks. which ignored many of the fine details that we know exist in real biological networks, and started to train them. As the similarity to more biological networks is this building the entire system for a large collection of simpler units. The simpler units do sort of simplified neuron-like operations, and learning is done entirely by modifying the strengths of synapses, the connections between elements. This is how learning is done. This is how we believe and have evidence for that this is what's going on in biological systems. This is what was adopted together with the backpropagation algorithm that changes the strength of the weights of the synapses, and this was basically how things were constructed. And the results were, in terms of performance, the results were really surprising, and the accumulating results are quite stunning. There are certainly interesting accomplishments that just by this training, changing the weights of neurons with a large body of training data, produced everything that happens around us in the area of application of AI, at least in the large majority. So things like automation. This is from a new assembly line or production line of Tesla, and you can see big factories with no people. They even mentioned recently, last year, there was a robot with deep learning that managed to assemble an IKEA chair taken out of the box, so this is certainly some proof for intelligence. More seriously, automatic diagnosis for certain diseases. This is from, I think, this year or 1917, or maybe even 18. There is work on in the health area on automatic diagnosis in a number of areas. This is in retinal images, which initially was the target was to analyze and diagnose some eye diseases, but they found during the research that doing this they could anticipate and diagnose not only retinal damage but also heart condition. Basically, your probability of getting a cardiovascular diseases better than most of the existing methods in completely non-invasive way. And here again, the training is, they don't know why exactly the machine is making these decisions and what exactly are what is the evidence on which it bases its decisions. It works after training it. You give it retinal images, you give it annotated data which people developed or had cardiovascular diseases, and the machine learned from this to predict cardiovascular problems from the retinal images. There was a student there who spent the summer project there and tried to use the same data to predict or to be able to tell what is the age of the person and what is the gender, is it male or female. There was no basis to assume that this is at all possible, that the retinal images of males and females, for example, would be different, and the results were with high success rate. They could really tell from the retinal images whether these are males or females, and nobody knows why. Nobody looking at the images and so on so far knows exactly what's happening. You simply train it again. Here are many images. We know the correct answer. These are males, these are females, and the machine learns to extract the relevant features, form internally the necessary rules, and do it. In this sense, it's certainly superhumans. Humans looking at these images cannot do it. There are the autonomous vehicles that Amnon just described, which are making are going to make great impact on our lives. It's not just cars. For example, this is a flying machine. This is an aircraft that lands on aircraft carriers, which is an extremely difficult task, but it takes off and lands down and does air refueling, and there is no cockpit. There is nobody there. It's all deep learning AI. Translation for me is interesting because it certainly looks like something that requires more higher cognitive understanding and so on. Translation, I don't know if people have tried it enough in Google, but Google translation the Google Translate, works now very well. It started already in 2006, and it worked reasonably well. It's very popular. They translate 140 billion words each day. And at some point, just in 2016, so 10 years after Translate was already in existence, they switched it overnight from whatever they developed using various techniques, which incorporated also some rules of the language rules, linguistics, and parsing, and so on. They simply switched to network-based algorithm, and the improvement was very noticeable. They didn't tell everybody. In fact, they switched it overnight without telling anybody, just to see what will happen, and was immediately a sort of enormous buzz. People who used it said something happened. So suddenly, the translation is working much, much better from before. When you measure it quantitatively, this change overnight, the improvement was about equal in terms of success rate and precision to what they got over the previous 10 years with a pretty large team that worked on the Google Translate system and introduced incremental improvements. So again, and here it's, I think, surprising and unnatural. There is no understanding, there are no rules of the language, there is no linguistics, there is no knowledge of the world which is incorporated in the translation process. The way that translation is learned in this case, you simply, there are enough databases in the world of books and articles and conversation in multiple languages being translated, so you simply feed it into the learning algorithm. Here's the input in English, here is the correct output in French. That's all. From then on, it's the learning algorithm takes over. So it's only based on this large data set in order to then produce seemingly coherent and even intelligent, I would say, translation from one language to another. They showcase even something slightly more sophisticated in which training or just big data seems even more sort of strange and insufficient. I don't know how many of you saw this. This was a couple of weeks ago in which Google showed the way that they can do automatic conversation in various domains, and this is from the video, so you will hear just a few seconds from the conversation, but this is a computer making a phone call to a hair salon to try to to book an appointment for a woman's haircut. And you will hear, just to help you, when you hear in a minute, you'll hear the sound. When you hear a person-like voice saying, I'm calling to book a woman's haircut for a client, that's the machine, and just follow the conversation. I'll just play a few seconds, and but see what the task is about. And if it's not playing, we'll give it up. No. Okay, so unfortunately the video does not seem to work. Okay, does not work. Too bad, but the conversation is very fluent and very convincing, and it's booking they're negotiating what type of service she wants and when and so on. It's you can look it up in it's available online. But here again, what may be strange is to realize how this is created. So there's nothing that is being programmed into the system or explained to this system in terms of what haircut is and what is a hair salon and what type of service she is requiring. It's simply training the system with hours and hours of conversations, in this case in the domain of hair salons. And now you can enter, or the system can enter a new conversation. It always branches and goes off in different directions, but the conversation is fluent. She achieves the goal. I'm not sure if the other party even can notice that the conversation was carried out by, not by a human, but by a machine. The story of Go, which was already mention, let me say a few words about it, because again, it's going more in a direction of sort of seemingly more intelligent performance. So this is a system that was mastered the game of Go. The game of Go, you know, people in the West do not usually do not know too much about it, but in the East, in China, Japan, Korea, this is a highly popular and highly appreciated game. It's a very complicated game. It's a very ancient game. There is written history of some 3,000 years written about this game. It's considered usually more complex and difficult to play well than the game of, even the game of chess. And it's a big cult, a big culture in these countries. There are books about it, there are schools about it, and for example, young children who show real promise in the game of Go, they very often they leave normal school and go to special schools for training the future Go masters. So it was quite a bold move to call one of the best players in the world, Lee Sedol from Korea, to an open competition, Google versus Lee Sedol. I saw an interview with Lee Sedol before that, and he's very nice and he's very modest, and he said, you know, it's too difficult for machines. He said that I predict that I will win 5-0, but, well, maybe it will be 4-1. And it was 4-1, but AlphaGo won. AlphaGo got 4 and he won. There was also a prize of $1 million. They wanted to make it attractive to the human competitors, but Google got the $1 million, so they're okay now. I watched a bit of it. It turned out, by the way, that this is the most watched event in the history of television, more than Super Bowl. 280 million watched it in real time as the game developed. And I saw bits of it, but luckily including this interesting piece. They keep, the Go experts, they keep the history of the history of the game, the great moves, and moves 37, game 2, entered the history books of Go. And the way it happened in real time was that the AlphaGo made its move, and the move is physically made by a person who gets the instruction and puts the piece on the board. And there was an annotator who was the American champion in Go. And when the move was said, he said, well, this is a mistake. Let's wait a minute until they correct the move. And he tried to entertain the people, the audience, with a couple of sentences going in some off direction. And then it turned out that it was not a mistake, that was the intended move. And the camera focused on Lee Sedol, and you can see that initially he's looking at it, and then you could see that he's stunned, and he then did something that is not done in these games. He got up and left the room and disappeared for about 15 minutes, just to try to understand what was going on. And he came back, and the game still went on for a while, but he never recovered from this move. And it's interesting that people then, experts, described it as a very creative move. And you wonder, I mean, is this something that, is the machine really creative? Is it something that we as people create? It's in the nuts and bolts of the machine, and we perceive it as creative, but it was expressed by various experts in the game when they described what happened and so on. They all use terms like very, very creative and very brilliant move. And this is where it becomes more and more interesting, that sort of the machines are trying to go cognitive. It's not just recognize images that this is a dog and this is an elephant, to do creative art and compete and then ask people which paintings are more interesting and more creative and more artistic and compete with humans. Here is a typical look at the title of the paper. This is a title in artificial intelligence, Unsupervised Funniness Detection. So this is looking at cartoons. I will show you an example in a minute, but try to decide which one is funny. Detecting sarcasm. This is also the title of the paper, Deep Networks, or Detecting Sarcasm in Social Platforms. Anyway, they try to detect which paragraphs are sarcastic. Let me skip this, the theory of mind. Here is what I mean. Here is a cartoon, and this is the public sort of competition that the New Yorker puts out. They give you a cartoon without a title, and the challenge is make a nice title for this cartoon. And the question, which one is funny? Here is one that the computer thought was very funny. But you can see it understood that there is a cone folder and so on. If that's for those, I'm not here, the bull is saying. So that's pretty nice. But do the machines really understand anything from what they're doing? I think that's now a big open question. I would say a $30 billion question a year, because $30 billion is what the big AI companies, Google and Amazon and Facebook and the big companies are putting every year in the research budget on AI. Compare it, by the way, the total research, the budget in the United States on scientific R&D, civilian R&D, not including what the military is getting, is 70 billion. That's what we spend on science and development in the US. Just the big AI companies on AI spend 30 billion. Anyway, we look at these images, and clearly what ImageNet would, as it is, would recognize objects in the scene. So it would tell you that this image has a piano and a person, and that's okay, but of course it misses what the image is all about, and to understand it you also have to know about gravity and about damage that can be caused and so on. And here it's not just cars and so on. We understand what's going on here, and that these two images maybe have something in common, some danger in that. So that's calls for some real understanding. So people are trying to tackle this, and there is an attempt now to generate, for example, automatic image captions. You're given an image, and the task is to generate a one-sentence summary of what's in the image. So this is going beyond recognizing the individual objects in the image. And some results, which are already being produced automatically, are not bad, as you can see here. A herd of cattle out in the field, so that's not bad, and the other one as well. However, I would say there is very limited success in this real understanding. For example, look at this image, whatever it is, and this was used to generate artificial caption, and the artificial caption was a brown horse standing next to a building. Now, this, in a sense, that's for ImageNet, that's great. That's winning the ImageNet competition. It really well, it missed the person, but it saw the horse and the building, and that's not bad. But certainly, it missed what's going on in the image. Here is another interesting one. So this is what the machine said. That's a man on a surfboard. And if you look at this, it's actually, if you saw surfboards and so on, it's not that bad, but that's what it produced. Compare it now with what a 5-year-old produced in this. So a 5-year-old said, this is a kayak. It's not a kayak, never mind. And this guy wants to throw a big rock on the kayak and make it sink and break it. Now, this 5-year-old sees the entire dynamics and agents, and the agent, it's an evil agent who has goal, and the goal is to do something with an object, to throw this rock. And I know that the anticipated result is that the rock, which is big and will be thrown at the boat, would break it and make it sink. So you see all of these things that are in the mind of the 5-year-old, and this goes in the direction, this is really starts to be understanding what's going on as opposed to what was produced here. Let me show you another example of understanding what's going on in the image in another person's mind, which is part of what's going on here. This is from the work of Warneken and Tomasello in Max Planck in Germany from 2006. I got it from a friend, Josh Tenenbaum, so thanks to him too. I hope that this works. See what happens here. It's an experiment with this little guy here. So watch what this guy is doing. Okay, so this is the experimenter. This is Warneken. See, he's frustrated but not being able to put it. Look what this little guy's doing. So this is truly, you can see that 18 months is pre-linguistic, he doesn't speak yet, but you can see how he understands the world in terms of what's going on in the other person's mind, what he's trying to do. It's certainly not big data. He's not seen many people trying to bump into a closet with holding some books in their hands and so on. So it's really real understanding. It's understanding social situations, people. It's understanding physics, trying to open getting into this closed piece of space, what you can do in order to help. So this, you can see the sort of the natural understanding that happens with very little training, very little big data. Now this is very connected to brain research because we know now about specific subnetworks in the brain that have to do, for example, with the understanding of other people's mind, what other people are thinking of, or what is the goal of some other people that we see behaving in the environment. And it's localized in the brain in a couple of areas. The main one, sort of a focus, it's not the only one, but the sort of one which is very specific to this understanding other people is the Tpj, the Temporoparietal Junction. It's sort of the junction of the parietal cortex and temporal cortex. It's a bit closer to the occipital, but anyway, in this area there is a piece of tissue, a piece of cortex, which is dedicated to understanding what's going on in other people. And if you, for example, inhibit it, people will stop understanding what the other people around them are thinking or doing. So it allows somehow, this piece of brain allows this 18 months old, somehow there is a machinery there that allows them to do something which at the moment still looks mysterious and difficult, to understand in a deeper way the environment without training on big data. I'm finishing in a minute, getting close. So we see here that there is something here that probably goes beyond what deep networks are. We have somehow, through years of evolution, we have this specialized Tpj with some kind of network, which I would be surprised if it's just a simple deep network architecture in the way we use it now, and it somehow allows the agents to, with very little training, to make sophisticated understanding of what goes on around them. And this is something that we have been modeling and trying to work on, and I will not discuss what we have achieved, but we describe a number of models, or models in a number of areas in which I think biologically plausible, more specialized mechanisms provide you not with the solution to the problem, but with a learning capability within a specific domain that will allow you, with very little training, to get sophisticated concepts which may be better to explain this kind of behavior compared to existing networks. So let me just mention, because not some people, when they hear the term evolution and learning, say that in some sense it's all one big problem. We happen to have limited lifespan, so some of the learning is done through evolution, but basically it's one big problem of you start from nothing, you see a lot of examples. Some of them your ancestors have seen, and some of them then you acquire personally, but together it's a big data that allows you to solve the problem. And I think that that's, without getting deeper into the problem, that this is not the right way to look at it, and there are two different learning problems here, because if you think about dividing in this way, you'd expect that if this is just one big learning and most of it was done here, and the agent, the person just complements it with his own personal examples, you'd expect that a baby would be born, if you learn to recognize horses, for example, with an almost operating horse detector, and you just need a few more examples to complete it. And this is not what happens, if you take this is not what will happen in models of learning, and it seems to be that there is a different problem of learning to create not an almost complete solution, but what you eventually do is you're not born with an almost operating host classifier, but you're born with an efficient general machinery that allow you to learn and recognize any group of object, any class of natural object that you might see. And the stages are not necessarily, or probably not, accomplished by a simple single solution of deep networks. Let me skip this because we are running out of time. So let me just end with the final sort of thought slide. We certainly have gone through, society, have gone through very rapid progress in intelligent processing, and the changes are transformative. We are going to see them everywhere. They are going to help us or to be part of our lives in many, many domains, and the big information companies will push it forward and will do their own work on making it more effective and working better. So this is certainly happening and will continue to happen. But do these systems really understand, the system that translates, the system that make the phone calls, the system that describe images and so on? This is an ongoing debate. As you could tell from the way I describe it, I'm more on the skeptic side. Some people out there and leading both companies and in universities think that this is basically the answer. We know now how intelligence works, and now we have to work more on these deep networks and train them on bigger data and making some improvements, but the debate is going on. As I said, I think that they are still not really understanding, and still that we are far from human brain and cognition, and there is a lot more to discover. And to discover, I think, both by looking at the human brain and human cognition, it will give us insight into what other mechanisms may be in play, and also, I think, computationally, we can develop new modes of learning, which we learn from less data and reach broader and deeper understanding. And finally, I should mention that what I described here is what I would call cognition, is solving problems and intelligent in this way. What make us, what make us humans, it also includes beyond this more analytic cognition, there are emotions, there are awareness, consciousness, and so on, which I'm not describing at all. What the relation of deep networks to this is even more debatable, and I believe that we will hear a little bit more about it in the final talk of this conference later on. So let me stop here, and thank you very much for your attention. Thank you.